what was noticed, one thing that's amazing is how science a lot of times gets better just by getting better at looking at things. So a little bit later, when we had ability to detect infrared wavelength better, ultraviolet wavelengths better, then we got the entire spectrum of hydrogen. And we saw a lot more lines, some higher energy lines and some lower energy lines. These are the higher energy lines, the Lyman series, and lower energy lines, the Paschen series. And there he generalized it to be 1 over lambda equals same constant, 1 over m squared minus 1 over n squared. Exactly the same constant. And for Balmer, m is equal to 2. For Lyman series, m is equal to 1, and for Paschen the Paschen series, then m is equal to 3. So this clearly includes the Balmer equation, but it generalizes it to a lot more possible integers. And as you can imagine, as people got better and better detecting things, they discovered lines corresponding to m equals 4 and so forth. So this was a little more satisfactory because it explained all the lines, and it explained why that weird 2 is there. The weird 2 is there is just because that was one of the possible ones, and it was the only one that was in the visible spectrum. So as you get better at looking at things, it becomes easier and easier to figure things out. So, oh yes, so n has to be greater than m, because otherwise you get 0 or negative numbers. That makes no sense. So one thing you might think sometimes, how do I know which one is n and which one is m? And the answer is going to be, well, whichever one, m is always going to be smaller. That's how you know which one is n and which one is m in the formula. Okay, so we have this formula. So what Niels Bohr proposed is, well, what we're seeing is that the energy has to be of certain levels. He proposed a model of the hydrogen atom as a nucleus with electrons circling around it, and only specific orbits with energies were available. So that's the case when an electron falls from a higher energy outer orbit to a lower energy inner orbit. In order for energy to be conserved, it has to emit electromagnetic energy whose frequency corresponds to the energy difference between the orbits. When you shine a light on an atom, if it happens to be the right energy, if it happens to be that energy that corresponds to the energy difference between two orbits, then it absorbs that light, or it can absorb the light. It doesn't always have to, but it is possible to absorb the light and then jump up to a higher orbit, where the difference in the orbital energies is is equal to the energy of that photon that's being absorbed, because energy has to be conserved. So what this did not do is explain why only specific orbits were possible. We'll get to that in a second, mostly next time when we talk about how matter can behave as both wave as a particle as well. And so, but if that's a physical picture that at least explains why it happens, that if the electrons orbit in only certain orbits, then that would explain the relationship between them. Doesn't explain why the numbers, but it would very clearly explain why you get line spectra. You don't have, it's unlike, a planet orbiting or satellite orbiting Earth, where by changing the speed, changing the kinetic energy of the satellite, you can continuously vary where it goes. Electrons can't do that. Okay, so that's what our picture, and then it turns out to be, it doesn't explain why, but it is consistent with what we see now, that the energy of photons corresponds to energies between electron orbitals. The Rydberg formula is just H, but the concept does apply to all atoms and molecules. It's just that for things more complicated than hydrogen, the formula is more complicated. And in a lot of ways, you can't write it out as a formula, but you can numerically calculate all of these. And we'll get into why it's more complicated later. Practice this a little. What's the wavelength in nanometers of the photon emitted when an electron drops from the 5th shell to the 4th shell of hydrogen? All right, so we've got our formula here. So first we have to figure out which one is m, which one is m. Well, m is always the smaller one. So m is equal to 4 and n is equal to 5. So 1 over 16 minus 1 over 25 equals 0.0225. Great, so we have 1 over lambda is equal to Rydberg constant times 0.0225 equals 0.0225 times 1.097 times 10 to the minus 2 inverse nanometers. Remember that that's the Rydberg constant, equals So 1 over lambda equals 0.02468 times 10 to the minus 2 inverse nanometers. I'll flip that over. 2468 would be 0.002468. Let's get this right. Let's 0.00. So instead of 1 0, there's 3 zeros. Do 468 nanometers input. 0.002468 inverse nanometers, which equals 404,050 nanometers. Quite long wavelength, well into infrared. One other way sometimes that can be useful to think about it is, it's lambda equals 1 over r. We're just flipping, we're doing the inverse here earlier. So 1 over lambda is equal to r times 0.0225. And so 1 over lambda is equal to 1 over r times 1 over 0.0225. And 1 over r is the inverse of the Rydberg constant, 91.13 nanometers times 44.4, which is of course equal to 450 nanometers. It's just whichever way you find easier to deal with. It gives the exact same information in the end. So these are relatively far out, so a relatively low energy transition, and therefore a relatively high wavelength, well into the infrared. And it's harder to observe these things because this is well into the infrared. So just the ambient heat can, that's coming, radiating from other objects can mess up the transition between the shells. So you have to do very careful experiments to be able to measure these wavelengths. So what we get is that there are discrete energy levels for electrons and atoms. Excited atoms have electrons raised to higher energies that relax and release characteristic discrete, not continuous lines of light. Only certain levels for E are allowed. So excited atoms have those electrons that can drop back down, or we can excite electrons with photons of exactly the right frequency of light, and those will be excited up. That's how we get the energy levels to move. There's energy levels within the electron, and we can use light within the atom that correspond to changing electron orbitals, and we can use light to probe what those energy levels are. In hydrogen, you'd see something like this, where you have some energy levels that are here, and it turns out that there's more energy levels at the higher. We can't see that from these experiments, but there are more. For multi-electron atom, and these are not on the same scales, you have different scales here, these energy levels start to change a little bit. The formulas are not the same because of interference from other electrons. So if you have single electrons, things are simple. If you have a lot of electrons playing with each other, the energy levels get very complex. And so we'll dive into next, now that we have talked about how the nature of light, and light can be used to probe the difference in energy levels in an electron, of electrons within an atom. We'll talk about why those energy levels